It's my great pleasure and honor to have been asked to come and give this talk this evening. I understand it's the first time a mathematician has done this. I suspect some people are rather afraid of asking mathematicians to give talks, but I will do my best. There will be a lot of pictures, and there will be a little bit of mathematics. So I hope there will be something for everyone in the talk. I'd particularly like to thank Dorothy Buck for both for her enthusiasm about the invitation to me and also for being a very wonderful and charming host, or perhaps I should say hostess, I don't know. So I'm going to be talking, trying to give you some flavor of the subject really I've been working on for many, many years now. In particular, some rather beautiful pictures, computer-generated pictures, which come out of this book, Indra's Pearls, which Sir Roy referred to. This is an example. So as the talk goes on, I will explain to you, or give you at least a little bit of a flavor of where these pictures come from and what they're about and why they might be so interesting. So I thought, well, I was actually asked to say something about my personal story. Now, Sir Roy's actually really summarized my life, but at least he didn't know this. So this was actually my first day at school, and it's rather a wonderful picture. I think I'm allowed to say this now. What you don't see from this picture, but the other picture on the other side shows that under my arm there's my favorite teddy bear. In any case, so I started life going to a little, really it was a dame school in the village where we lived, but I was very fortunate to be able to go to, after a couple of years at the dame school, after a couple of years at the dame school, I was very fortunate to have most of my education at Oxford High School for Girls, which was a truly good school. This is us on our 25th reunion. So you can see it was a girls' school, and I thrived in the atmosphere there. I think because there were no boys, there was no question somebody was going to do maths and science, so some of them were girls. I don't know, some of you may notice this in the middle, you may recognize, that this is actually Dame Mary Warnock, who for a brief period, while I happened to be in the sixth form, was actually headmistress of the school, and she was an extremely inspiring figure. I was very lucky that she was there. We also had some excellent maths teachers, and as Sir Roy said, I actually, when I suppose I was about 12, I really fell in love with Euclidean geometry, and I found I was rather good at it. And I made it my secret ambition that I wanted to go to Cambridge to study mathematics, and really secret was that I wanted to get a first-class degree, but I think you're the first people I've told publicly. Well, in the event, I more or less achieved my ambition, modulo the fact that actually I went to Oxford, as Sir Roy said, rather than Cambridge, so here we are at Somerville College. When I arrived at Somerville, I suppose, Somerville at that time, of course, was a women's college. I suppose something like about 10-15% of the mathematics students at that time in Oxford were women. It was actually, I was a great fan of being in a women's college. It was very nice to be in a small group of women. It wasn't quite so intimidating. We were taught by tutors who were women, and it was sort of an introduction in a gentle kind of way to the wider world. From there, Sir Roy told you, I went on to Harvard. This is a picture of the famous Science Center at Harvard, which actually opened the precise moment when, in fact, when I first arrived there early in the summer, it didn't exist, but by the time I got back there in October, it was open. I then went on to Berkeley and had a year in Cambridge. And I was then very fortunate to get a permanent job, permanent lectureship in Warwick University, which at that time was really the center for dynamical systems and chaos and this strange subject, ergodic theory, which I was working on and which nobody at Cambridge seemed to have really very much interest in at that time. So when I arrived at Warwick, I think there were about 25 or so permanent staff. I was the only woman, but I immediately found myself very accepted. It was a very sort of open, democratic place. I felt as if everybody played an equal role in what was going on. But of course, it was rather nice. Sometimes one wanted a little bit of female company. So I was very pleased when in the early 1980s I met Joan Berman, who you see here, who was a professor at, or still is a professor in Columbia University in New York. And we started on a very productive and lengthy collaboration to do with curves and hyperbolic geometry and a little bit of dynamics. She was a topologist, I was a dynamicist, and I will explain a little bit in my talk how these things fit together. But we stayed with each other in each other's houses. We enjoyed a lot of time. We learned cooking from each other, and we gossiped. And I think, of course, I got on very well with my male colleagues, but I have to say that I don't think I could have had such a close and productive collaboration in quite the same way with someone who wasn't of the same sex, let's just say that. So Roy also told you about this organization, European Women in Mathematics, which I was involved in founding in the 1980s. This was a huge amount of fun, brought together women from all the countries in Europe in the very broadest possible sense. We weren't at all confined to the EU or whatever it was called then. And here we are in our third annual meeting, which I organized in Warwick. So I got an awful lot of companionship and inspiration and friendship out of the other women involved in this group. Now, the next slide I wanted to show you on the right here, this is, I'm sorry, Professor, sorry. This is David Mumford, I'm sorry, famous. Things never behave the same way when you do them in a different setting. Right, David Mumford, who, he in fact had been my first advisor when I arrived at Harvard. On the left, you see my colleague Miles Reed. But in any case, Mumford at that time had become, I give up, Mumford had become very involved in, I will sit here like this. Mumford had become very involved in drawing these rather beautiful computer-generated pictures, such as was on my first slide, and invited me to join in writing this book. Well, I'm sorry, I give up. The next picture is showing not only was I involved in writing this book, at the same time I was involved more and more in developing the mathematics that lay behind these pictures. And in 2003, I was privileged to run a program at the Newton Institute, at which essentially all the key people working in the field I'm going to touch on in my talk came together. This is our conference picture. You can get a sense, you can't really see, there are a few women in the picture, but you see mathematics is a pretty male subject, but there's space for women. People always are very encouraging, and there's no problem at all, but it's just a fact of life that most mathematicians, at least at the moment, are men. The last slide is just to show you, I thought this was a nice slide to finish on. European Women in Mathematics is still going strong, and we're having a conference this August. It'll be our 14th meeting, and it's going to be held in Novi Sad in Serbia. I had no hand in making the poster, but I just thought it was kind of appropriate for this talk. So that's my brief potted history, and let me now come on to my talk proper. So I hope I can manage to convey a little bit of all these things. I want to give you just a flavor of what is hyperbolic geometry about, what have surfaces got to do with hyperbolic geometry. This is what I worked on with Joan Berman. We'll then make an excursion into 3 dimensions. I will explain a little bit how these beautiful images that are the topic of our book, our fractal images, come up, and then spend a little bit of time on some very exciting recent developments that have entered into, closely connected with what I've been doing all these years. So I thought we should start back at the beginning. I'm sure everybody knows about Euclid, and I'm sure everybody knows about Euclid's famous fifth or parallel postulate, which states that if we're given a line, L, and a point P not on L, then there's exactly one line through P which never meets L. It can be stated in different ways, but this is maybe the easiest way to say it. But how do we know this is true? Because the statement involves you following along this line forever and ever and ever, and how do I know that I won't eventually hit L? And so for centuries, indeed millennia, people worried about this issue. And all sorts of interesting mathematics, geometry was actually developed in the course of people trying to see whether they couldn't deduce this axiom from other what seemed much more self-evident basic assumptions of Euclid. And in fact, it went on puzzling people for about 1.5 millennia. And finally, around 1820, these 3 gentlemen independently realized that the reason that you couldn't prove this postulate was that actually you could have perfectly good geometry in which Euclid's parallel postulate was no longer true. This was a truly shocking discovery with huge philosophical implications. In fact, Gauss probably discovered this considerably earlier than 1820, but he was so reluctant to go public, he didn't want to cause controversy, and he knew how hot an issue this would be. In any case, this is just a picture to show what they started with, as it were, a fresh piece of paper and said, right, let's do geometry in which we don't assume the parallel postulate. Let's see what we can deduce. So here's our line L and our point P. What if there were lots of lines through P not parallel to L? And so one particular consequence which actually has significance for chaotic dynamics is that 2 lines which don't meet come together at some nearest pair of points here, but then they, instead of going along forever at the same distance apart like railway lines, they actually diverge from each other exponentially fast. So here is rather a nice picture. This is a very famous quotation from Bolyai, who wrote home to his father, who was also a mathematician. I've discovered things so wonderful that I was astounded. Out of nothing, I've created a strange new world. And maybe this is a sort of, this is what mathematics is like somehow. You discover something, and then out of it comes enormous consequences that you would never have imagined. And I think if Bolyai could see the things which I'm going to now tell you, he would be truly amazed. The picture is from a lovely little book by someone called Marta Sved, which is explaining this business about Euclid and the parallel postulate and so on, sort of for children, all in terms of very delightful pictures based on Alice in Wonderland. And the point of this is you can see here the table, its edges are 2 parallel lines, but the lines are sort of diverging from each other. So what is hyperbolic geometry? Well, the philosophers went on arguing for a good 50 years after Gauss, but it was really understood by at least a small group of mathematicians by the middle of the 19th century that actually hyperbolic geometry wasn't so strange, because really it was nothing other than geometry on a surface which is everywhere saddle-shaped. So here's a little saddle, and we're just going to do geometry on this surface, just like cartographers are doing geography on the surface of a globe. And it turns out that the fact it's everywhere saddle-shaped means that it actually, in the large, looks something like a leaf of kale. Actually, there are lots and lots of natural objects which grow in this way. And I think this is something which really still hasn't been fully exploited, that natural things often exhibit this kind of geometry. We don't quite know what to do with it yet. Here is another picture, and one thing I wanted to highlight was the fact that this triangle and this triangle look a bit thin. What does that mean? As if the sides are sort of pulled in somewhat towards the center. Remember that, we'll come back to that. So, well, how do we study this? Just as cartographers project the globe onto the plane, so we project this curly hyperbolic surface onto the plane. There's various ways of doing it, but one of the ways which I prefer is called the Poincare disk, and we actually project everything to the inside of a disk. And lines, geodesic lines on this kale-like surface in this projection come out looking like circular arcs which hit the boundary here at right angles. And so angles are all right, but shapes get distorted. You can see this in this picture. This is a tiling of the hyperbolic plane, but all these shapes, although they look as if they're getting smaller and smaller as you go out, actually they're really all the same. It's just the effect of the projection that makes it look peculiar. Another feature of hyperbolic geometry, if you sit and stare at this picture, you can actually calculate the number of tiles in each successive ring, and you find that unlike what would happen in Euclidean space the number of tiles grows linearly with the size of the ring. Here it grows exponentially with the radius of the ring. So this is a feature of hyperbolic space, and I want now to show you a rather beautiful video which really explains this infinite nature of this thing. Peter Lieper is a retired engineer who does superb mathematical graphics. I don't know how he does it, but let's see. So we are flying over the hyperbolic plane, watching this tiling, and you see as you get nearer to a tile, it gets larger, and out there at infinity, the horizon is forever receding. So this picture, it looked like it was finite in a disk, but actually it's going on forever and ever out to infinity. So let me say a couple more things about basic hyperbolic geometry, and then we'll go on to surfaces. So another feature of hyperbolic geometry, many of you probably know the angles in a spherical triangle add up to more than 180 degrees. I'm sure everybody knows that angles in a triangle add up to 180. So angles in a hyperbolic triangle, you have to measure in radians, but they add up to less than 180. And there's a formula which is kind of the opposite of the formula on the sphere, that the area of the triangle is pi minus the angle sum. And the point I really want to make with this is, because we aren't rigidly constrained to have the angle sum being a particular fixed value, we've got lots more choices for tiling. So here is a tiling in which we start with a basic triangle whose angles are pi over 2, pi over 3. Now, if it was Euclidean, it would have to be pi over 6, but we make it a bit less. We make it pi over 7. And you see the effect is, at this point, at the red dot, we've got 4 things meeting, and they add up to 360. At the green dot, we've got 6 angles of pi over 3. That's all right, 360. At this dot, if you count, there are 14 tiles. And the 14 tiles, each with angle pi over 7, gives you an angle of 2 pi. And that would be completely impossible in Euclidean space. And this is why there's so much more flexibility in hyperbolic space. It can be sort of infinitely fascinating. I want to just digress for a second to tell you a story I think is rather funny. When my colleague, Professor David Epstein, was many years ago now involved in some very exciting developments in hyperbolic geometry, and a reporter from the Coventry Evening Telegraph got to hear about this. So he went over to interview David. And so the piece came out in the Evening Telegraph, and this is sort of the danger of popularizing mathematics. It said, Professor Epstein of Warwick University is working on hyperbolic geometry. He has proved that the angles in a triangle add up to 179 degrees, and he is working on getting it even less. So that's what hyperbolic geometry is, right? Right, now there's one more thing I want to say about triangles. I'm going to go on about thin triangles, and don't worry, this is the most mathematical of all the slides that I have, and you aren't really suspected to work this out, but here's a right-angle triangle. There's a version of Pythagoras' theorem. I'm sure everybody knows Pythagoras' theorem. Here's the hyperbolic version of Pythagoras' theorem involving, coincidentally, hyperbolic cosines. And if you play with this formula, you might want to know the distance from this side, this vertex C, the right angle, to the side AB. Of course, you drop a perpendicular there and do a bit of trig. You can do a hyperbolic trig. And it turns out that whatever the triangle is, this distance is always less than a number. We don't really care what number. It's less than a number. And this is dramatically different from Euclidean geometry, because in Euclidean geometry, you could double the size of the triangle. Well, then the distance from here to this side would double. So this tells us that in hyperbolic geometry, you can't have similar triangles. If you've got the same angles, they're going to be congruent, which is completely different. One of these wonderful things Bolyai was talking about. Another consequence, even more striking, I'm sure many people here know the triangle inequality, that the side C's, it's quicker to go across the diagonal than to go around the two sides. Actually, in hyperbolic geometry, you gain very little by going across the diagonal. You gain at most this factor, this additive number. So actually in hyperbolic geometry, really going from here, from A to B, you almost might just as well go here. Independent of how big the triangle is, you're never going to gain more than this constant amount of distance. And this is one of the things that somehow makes hyperbolic geometry go. It's really an important thing. And here is a sort of more accurate statement about thin triangles. It follows that on any triangle, right-angled or not, I can find a point on one side which is at distance at most this magic number, which is called Schweikart's constant, I believe, from points on the other two sides. So again, completely different from Euclidean geometry. In Euclidean geometry, if you scale your triangles, obviously it takes the distance from a point on one side to the other two sides gets larger and larger. Hyperbolic geometry, somehow there's a part of the triangle that has a strictly finite diameter. Well, I shall come back to this near the end of the talk. So I want now to go on to talking about surfaces. And I should have probably said at the beginning that the majority of the pictures I'm showing, in fact, come from our book, Indra's Pearls. In particular, this. Most of the pictures we made ourselves on computer, but we felt that certain things were beyond us, so we enlisted the services of a cartoonist, Larry Gonick, to draw some nice pictures. So what's hyperbolic geometry got to do with surfaces, and why is it interesting? So I want to first go back to something I'm sure that many of you, probably everybody here, is familiar with. In Euclidean geometry, we start with a square or a rectangle, and we fold it up and glue it up and make a cylinder, and then we fold it around and glue it up, and we make a donut or a torus. And one reason why this is a good thing to do is because it's very good for studying curves on a torus. So going along with a square, I have drawn here a tiling of the plane and a line across the plane of some slope. And all the sort of places where the line falls into the square have been transported back into this square and then drawn here glued into a cylinder, glued into a torus. And you can see what happens here on the torus is I get a glued up closed curve. And the point is that if I'm trying to study curves on a torus, from many points of view, it's much easier to study lines on a plane. I mean, anybody can study straight lines on a plane. You get kind of mixed up going around the torus. And this is actually a very important thing. This picture up here, this tiled picture of the plane, is called the universal cover of the torus, and it kind of unwraps stuff on the torus so you can see it laid out nicely in the plane. Well, suppose we want to make a more complicated surface. We don't want to do a torus. We want to do something else. There's a picture here of an octagon, and I'm sure many people who've studied basic topology may have come across this. If you would just take an octagon and glue up sides according to the colors, there's 2 purples, 2 reds, 2 oranges, and 2 kind of blues. If you play around with that, actually, this is kind of like 2 torus pictures divided by the line from there down to there. And when you glue it up and you follow the pattern round, you find you get a double torus. And these vertices have all come together at one point. Now, if we want to make a nice geometry on this surface, if we made this a Euclidean octagon, you can figure out the angle in a Euclidean octagon is 135 degrees. So if I glue together 8 times 135, whatever I get, it's not 360. However, because of the added flexibility in hyperbolic geometry, you can make an octagon whose angle is 45 degrees. And then when I glue up 8 of them, of course, 8 times 45 is 360. So I glue them up and they all fit together nicely and make a nice smooth surface. So this surface, in some natural way, carries with it hyperbolic geometry. If you lived on this surface and you looked around you, you would believe space was hyperbolic. Lines would diverge exponentially fast and triangles would look thin. And this next picture is a picture of the associated tiling, the universal cover. It's a rather beautiful picture of, there's an octagon here made out of some triangles, and then the whole thing gets reflected around to make a tiling of the hyperbolic plane. And of course it doesn't look it, but this has got the infinite property of that video I showed you before. Well, you can actually, it turns out that every surface more complicated than a torus, you can also, in a similar way, make out of hyperbolic geometry. And why is this interesting and important? Well, it gives you a fantastic tool for studying surfaces. And this was realized, I suppose, in the 1920s. People began to study geodesic flows on these surfaces. And because lines diverge exponentially fast, that means if I start at 2 events, as it were, very close together, and I move a little bit, very quickly, there's no trace of my history. Things spread out very fast, but of course, because the surface has got a finite shape, eventually things have to come back and come near themselves, but in some very complicated, random kind of way. So it turns out that geodesics flowing on this surface is a beautiful model of chaotic motion, the butterfly effect. You can understand a vast amount of detail about the butterfly effect, and the first models of this kind of motion showing it's possible were done in the 1920s using exactly this picture. And actually what Joan Berman and I were doing, and also I myself, was studying the sort of combinatorics of this picture and how it could give you information about curves, trajectories on these surfaces in much the same way as we could study straight lines on the Euclidean plane with a square tiling. So we could study lines across here, and there would be trajectories of some chaotic motion, but of course it's all vastly more complicated and fascinating, and somehow you never quite come to the end of this picture. So now what I want to do, this was the 1920s. I want to skip ahead to higher dimensions, in particular 3 dimensions. And really this brings us, well, there was sporadic small amounts of interest in this, but this is really skipping ahead to work that took off in the 1970s. So there's no common English word for the higher dimensional analog of a surface. It's called a manifold. Actually, I was quite amused when I was looking on the web for 1 or 2 things to prepare the talk. I was looking at something about manifolds, and up pop these little advertisements, of course, and they're all advertising engine manifolds. They don't quite know what they're doing, right? But anyway, I think it does come from the fact that an engine in a car is a tremendously complicated 3-dimensional shape, and that's what a manifold is. So we say that a manifold has a hyperbolic structure, or is hyperbolic, if on a small scale it looks like a piece of 3-dimensional hyperbolic space. And understanding this and other possible geometries you can have on 3-dimensional space has been a really major theme of mathematics in recent years, as I shall go on to show. So the local structure, well, here's actually quite a nice picture. If you look on the web now, you can find patterns for crocheting your own piece of 2-dimensional hyperbolic space. You can crochet coral reefs and things. I guess, you see, crochet is very set up for being hyperbolic, because all you have to do is cast on more stitches. I don't know how many people here have done crochet, but you just have to cast on too many stitches every time you go around the edge, which sort of explains why your crochet goes all kind of floppy, and you're really making a hyperbolic surface. Well, I'm sure many people have heard of the amazing progress made in recent years about the Poincare conjecture. So the Poincare conjecture is really about not the local geometry of the manifold, but its global geometry, what it looks like in the large. So from knowing what it looks like if you're a little fly, you don't really know how many loops and curves there are. Topology is about closed loops in the manifold, and not really individual loops, but we allow ourselves the freedom to pull loops tight, to shuffle them around, technically to homotop them. So you can move them continuously from one to another, but what we're interested in, loops that can't be any more tightened. So if I took a torus and I made a loop going around it that way, that was a torus, if I go a loop around there, I can't tighten it anymore. It won't ever pull tight to a point. So in 3D, this is a very complicated question, and the Poincare conjecture, the question is, supposing you have a 3-dimensional thing in which every loop can be pulled tight to a point, can you be sure it's actually a 3-dimensional sphere? And this is a question which tortured mathematicians for a good 100 years. I'm sure it probably led to suicide. It certainly led to madness and any number of false attempts. But Gregory Perlman, in a most amazing and fantastic piece of work, resolved completely this problem. And actually, I don't really want to get into his solution, but essentially it involved somehow putting a geometry on the manifold. You start with any old way of measuring a distance, and then you smooth it out and show that by the nature of things, eventually you have to land up with a spherical geometry, and it has to be a sphere. It's not quite true. Well, I don't know if everyone knows the Fields Medal is really the mathematical equivalent of the Nobel Prize, except that it's given to a mathematician who has to be under 40. Once every 4 years, several prizes are awarded. Actually, Perlman declined to accept the prize, but I mean, you know, he morally won the prize, so he didn't accept it, but anyway, he won it. So, yeah. Well, that's the three-dimensional sphere. In fact, prior to Perlman, much more complicated three-dimensional manifolds. The whole study of three-dimensional manifolds had somehow got a bit stuck. And William Thurston came along in the late 1970s and began to completely revolutionize the subject by discussing geometric structures on manifolds. So he started out by showing that just from some basic information about the loops on the three manifold, what the structure of the set of loops was, he could show that these manifolds actually were hyperbolic. So I've told you what 2D hyperbolic is, so you just imagine what 3D hyperbolic is. And he actually conjectured a conjecture which has now been proved, that every three-dimensional manifold can be cut up in a natural way into 3D, into geometric pieces. Well, let's move on. These are some pictures of tilings of three-dimensional hyperbolic space, rather beautiful pictures from a movie made by some of Thurston. Well, I'm sure Thurston had considerable input into this. Let me move on. You can make a three-dimensional manifold by starting by a three-dimensional polyhedron in hyperbolic space and gluing up the sides. But I want to talk a bit about another way of doing it, which is the following. I start with a plane. Has my piece of paper disappeared? Ah, somebody's tied it up too much around here. Can you give me a piece of paper? Right, thank you. Right, you start with a flat piece of paper, and you start bending it along a line. And you make a number of parallel bends, like this. And you see, you make them parallel so they don't bang into each other. And you start with it flat, and you gradually bend it and bend it and bend it. And you do this in hyperbolic space, not in Euclidean space. If you do it in Euclidean space, because of Euclid's parallel postulate, there's not much choice about what you do, and you get what's called a pleated surface. So my skirt is a pleated cylinder. It's a perfect pleated cylinder. In hyperbolic space, it's a whole lot more interesting because there are lots of parallel lines through points which don't meet. And if you do this procedure very carefully, you can sort of distort a tiling of the hyperbolic plane into a tiling of hyperbolic 3 space. Now, I don't really have time to explain in detail about this, but the main point I want to make here is this bent up plane. You see around the edges, it kind of comes to an edge where it goes off to infinity, and round the edge here, you get a very complicated shape, which is called the limit set of this, well, really symmetry group or three manifold or whatever it is you want to talk about. So this is one way to approach these beautiful limit set pictures, which are the topic of our book, Indra's Pearls. So let me show you some more pictures now. These are all things that you can get by bending along carefully chosen lines. And what is a fractal? Well, this nice little video shows you very well what a fractal... sorry. Oops. Right. Here we go. So this is tracing out this curve in the manner described in our book, Indra's Pearls. And what it's really doing is just going around the boundary of this sort of bent-up hyperbolic plane according to a very precise algorithm that you have to buy the book to see what it is. And what you will see is once it goes around and joins up to itself, we're then going to do some zooming in. Right, now we're going to zoom in. A fractal is a thing which, if you zoom in and look on a finer level, you see the same thing. And here you are going several levels of zooming in, and every time, not necessarily the precise pattern, but the general sense of the pattern repeats. That's a fractal. Well, I think I have to... more discussion in our book. There's the... it was our hope in writing this book that people would take up the interest in making these pictures. And one particular person who's done this superbly is another mathematical graphics artist. I think he's another retired engineer. he has a fantastic gallery. He's done all these beautiful pictures of sort of artistic versions of what we describe in our book. Now, I don't know, I think I'm running out of time, but let me try to tell you very quickly. I want to just say something about the astonishing recent developments which have happened and my particular interest in them. So you go on bending and bending and bending. And one possibility, eventually something has to give. Something bumps into each other. One possibility, which is very fascinating and which I first got drawn into, are beautiful pictures like this. Something has banged into something. Something has bent and bent and bent, and the angle's gone to pi, and the curve has gone to length 0. And here's a rather simpler picture. The limit set sort of fragments into lots of beautiful chains of circles. Now, I don't really have time to talk about this, but the second possibility is yet more fascinating, that from a thing that looks like this, which is a kind of like a crab nebula or something, this is a pretty bent up thing. If I bend carefully enough in a complicated enough way, all the yellow stuff inside this curve disappears, and I'm left with a thing like this, which is a mathematical object called a dendrite. And for those of you who know what it means, the Hausdorff dimension of this thing is 2. It's a sort of totally thick set in the plane. It's a very, very complicated and fascinating set. And what actually is going on, this is somehow associated to a three-dimensional manifold, remember. What really is going on, and all the different possibilities, has been unraveled in the last sort of probably 8 or 10 years. Our understanding has gone from it being rather a mystery to really knowing what's actually happening. So let me very briefly, I wanted to bring in Gromov. The path to understanding goes through a most wonderful abstraction of hyperbolic geometry made by Misha Gromov. Now, Misha Gromov, to my mind, is perhaps the most extraordinary mathematician alive today. He truly amazing ideas. He has just been awarded the Abel Prize, which was set up by the Norwegian government in 2002 as for historical reasons, which I won't go into, some of you no doubt know, but mathematicians are never awarded the Nobel Prize. You can't win the Nobel Prize in mathematics. There was this prize, the Fields Medal, but that's for young mathematicians. In 2002, the Norwegian government revived a very old idea they had to establish a prize which would be on the same level as the Nobel Prize, but specifically for mathematics. And I'm quite delighted that this year's recipient of this prize is Gromov, and in fact, his award ceremony was exactly a week ago today. So he had many, many incredible ideas. One of them is the following. It's a sort of abstraction of hyperbolic geometry. So we're going to study a space which we really know very little, except we can measure distance, and triangles are going to be thin. Okay? And triangles going to be thin means that there is a point in the triangle which is a bounded distance from all the three sides, and the only difference with ordinary hyperbolic space is that the bound doesn't have to be log of 1 plus root 2. It could be anything. It could be 1,000,000, but it's some finite number, and it's independent of the triangle. And Gromov recognized, of course you can make a definition, the point is he recognized that that was sufficient to capture all the features of hyperbolic geometry that one wants to work with. And Minsky, who was a student of Thurston, made further remarkable progress by the following, solving this problem of what these degenerate limit sets are. You make a graph in which each point, each vertex, is a loop on a surface. And you join two points by an edge if the loops are disjoint from each other. And Minsky and his colleague Howie Mazur were able to prove that this immensely complicated thing is a Gromov hyperbolic space. It's certainly not ordinary hyperbolic space. They proved it was a Gromov hyperbolic space, and armed with that, they were able to show that the set of, or Minsky and his co-workers showed that the key determinant of our hyperbolic three manifolds are the loops which aren't too long, and knowing what they knew about Gromov hyperbolic spaces and these curves being a Gromov hyperbolic space, they were able to show all the possibilities and how you could completely reconstruct these manifolds out of just knowing about geodesics in this Gromov hyperbolic space. So I don't have time to go into this more. A couple of pictures, again, this is something that puzzled me for many years, studying these limit set pictures. There's a beautiful chain of circles here, which if you go through a sequence of such pictures, seems to converge on this. Well, I was never able to prove this, but very recently I've gone back to it, armed with the knowledge of what Minsky has done, and armed with Minsky's information, managed to prove with Makoto Sakuma that this convergence that looks like it happens. So I just want to end with another nice video made by David Wright, again based on our algorithm from Indra's Pearls, drawing this much more simple looking limit set. So here we go. This is a nice little video here. So again, you're going to see our algorithm drawing this very complicated curve, and you're going to see zooming in. So I should set this to music. But I've brought a copy of the book with me, so if anybody would like to have a look at it after the lecture during the reception, you're welcome to have a look. So perhaps what I can end by saying is that I hope I'll convince you, well, on the one hand, mathematics is fascinating as mathematics, but actually there's something extremely appealing about these kind of pictures. And now we have such wonderful ability to do computation and graphics that somehow all these things that previously only existed in the imagination of a very small number of people, now you can kind of see, of course you don't see all the detail, but you do at least get some flavor of maybe why we want to spend our lives just staring at these pictures and wondering about them. Right. Thank you very much.